Good evening and welcome to Chain Southwest. My name is Nick Valentine and I'm the founder of Chain Events. I'm not going to speak much as I know you want to hear from our fantastic speakers. So, this event has been organised by a number of the young member organisations in the Bristol area. And tonight we're here to share knowledge and experience. It's about cooperation between the institutions, building a community for young engineers, promoting the benefits of your engineering institutions, and providing continuing professional development. So, our agenda for tonight. You can see that in front of you, and there will be time to submit questions. If you have a question, please submit these through the Ask a Question function. And if you want to ask a question, please include the name of the speaker that you want to ask a question to. So these are the organisations that we've got speaking tonight. And if you would like to get more involved in Chain Events, please visit our website. Basically, this is all about getting you to know the engineering institutions in your local area and getting more involved in them so that you can reap the benefits of involvement and continuing your own professional development. So our first speaker tonight is Martin Belshaw, and he's the president of the Institution of Measurement and Control. He will be introducing our event. So without further ado, I will pass it over to Martin.
Good evening, everybody. In 1833, an eminent Scottish physicist once said, "In physical science, the first essential step in the direction of learning any subject is to find principles of numerical reckoning and practical methods for measuring some quality connected with it. When you can measure what you are speaking about and express it in numbers, you know something about it, otherwise you don't." This was an awful long time ago, and although we could probably calculate the water that has flowed under the bridge since then, riverbed profile, depth, and so on, we won't. Necessity has dictated many of the advances in technology. Nowhere is this more apparent than the discipline known as instrumentation, practically unknown 50 years ago, when manufacturing instruments was akin to watchmaking, but in most plants the main job of the instrument engineer was to clean plugged sensors and fix jam control valves. The control panels of the day were full of push buttons and manual loading stations, and the operators were an integral part of the control loop. Over the years, instrumentation has evolved from discrete devices developed to fulfill specific needs of measurement and control to a science in itself where the economics of entire plant and processes are based on sophisticated control strategies and instrumented systems. Today, when we use multivariable envelope algorithms to optimize complete plants, when the control theory of our industries has spread from military to medical applications, and when we block operators from overriding or deactivating automated safety systems, those early years are now confined to the history books. About this time last year, I was invited to a parliamentary briefing along with lots of IT-savvy farmers and some boffins to discuss applying control and automation technology directly to both livestock and arable farming, to realize efficiencies previously only farmer fantasy. It is called precision agriculture, a largely hidden and unknown facet of instrumentation and controls industry. The main challenge is feeding the world in the next 20 years against a backdrop of relative decline in production efficiency over the past 30 years, caused through a break in the link between production and fundamental science, or rather, too great a focus on biology than on measurement on the farm, which is where automation and control might step in. We need to see yield increases of 70 to 80% globally to redress this, and precision engineering has the potential to be the most disruptive technology available to modern agriculture, as disruptive as biology was before. Both agriculture and engineering sectors must respond to the challenges of feeding a rapidly growing population sustainably. Research and development is vital to addressing this challenge, but agri-tech is likely to play a vital role too. In short, Networks of sensors connected via the internet, making SCADA on the farm a reality. An internet of agricultural things, so to speak, seamlessly linking producers, vets, and advisors into an integrated feed growth environment, its monitoring system being no different than the MIS systems the big oil and gas and farmer operators are using already. Robots do the milking, monitoring food in and out per cow, checking on welfare, administering treatments at the same time. Likewise, robots do the feeding, and 3D precision imaging, both production and processing, record the patterns of growth, capture the variance, weight gain and/or indication of disease, and calculate the all-important dead weight on the hoof, which itself becomes a control variable. An integrated on-farm data platform would provide services such as optimization of feed mix, reduction of waste, management of greenhouse gas emissions, fertility, weight gain, fat content, feed analysis, energy and eating periods, and collating and collecting milking robot output. Innovative sensors, robotics, data analytics, and systems integration projects will become key players in the future of agriculture. The Internet of Farming, a systems approach to agricultural efficiency, re-establishing the link between science and progressive agriculture. The Internet of Cows is not wishful thinking, it's for real. A collar, a pedometer, a tail tag comprising ultra-low power sensors, processors, transmitters akin to wireless mesh systems that we use today in the other process industries, provides real-time data for decision support in precision farming. Using the latest sensor technology to understand whole chain efficiency has the potential to radically change the efficiency of food production. It is not what we see, it is what's in the gaps of what we see where the real efficiency opportunities lie. Put briefly, the weather is the process noise which you can filter out. Historical data provides models for advanced predictive controls, and the rest is no more complicated than everyday process plant, where the beasts and the crops are the process. This is food for thought, surely. But on now to the more serious aspects, and that's our institute. Our institute has changed also in this time, and there have been various incarnations of the Journal of Measurement and Control. There has been the internet, and with it websites, and with this, all of the journals ever written available online for anyone to see. And we now have a new magazine called Precision, more at home on your coffee table than in the workplace. Today we see total dependence on measurement and control. Everything relies on this technology and the engineers, technicians, and technologists who design and build it. Meantime, there is particular pressure from technological change, and through the Institute, engineers can keep abreast of the latest and greatest, more or less in real time as it happens. The Institute of Measurement and Control brings together and represents engineers across all industries and academia to influence future technological developments. Similarly, he has input directly to government policy through papers, advisory groups, and manifestos to hopefully see right done. Membership of a professional engineering institution is essential to career development. It provides opportunity for networking and for professional recognition among peers and further afield. At the InSTEM-C, we provide a national network of local sections to facilitate this. It is particularly important for young engineers to develop, learn, interact, and raise their personal and professional profile. Additionally, we have embraced the call from the Engineering Council for CPD to be an integral part of Charterdom. We provide encouragement to continue the learning process, record CPD, and some members are starting to register via My Career Path. As part of this encouragement, can I suggest that the rest of you might do the same? As with most PEIs, there have been trials and tribulations, and we have had our fair share of restructuring, reshaping, rationalization, and some very scary moments along the way. But I like to think these are all sorted and we are pointed in the right direction, and our future is bright. 50 plus years ago, I was 10. I knew what I wanted to do, just not what it was called. When I first sat at Gower Street, you had to sign a leather-bound book with rainbow patterns down the pages. Looking back through its pages, it was full of engineering greats. The UK is desperately short of engineers. We should all take this on board and inspire those behind us to solve the problem going forwards and make more greats. Right now, I believe we have some of these in the making, right here, listening tonight. Thank you very much.
Thank you, Martin. So I knew we had a wide range of topics being discussed tonight, but I didn't think we'd be hearing about the Internet of Cows. But it really does show that these technologies are pervading every single industry. And in true chain style, we're now going to go from the Internet of Cows to air-breathing rockets with John Williams.
All right, thank you, Nick. Right, it's been a long time coming, but it's a privilege and a pleasure to be able to present tonight. It's probably been 2 years to get to this stage for me, for one thing or another. So I used to work at Reaction Engines. Oh, let's get to the next slide. So I used to work at Reaction Engines for 7 years, so I've recently moved on. But I can say it's been a great place to work. There's probably no place in the world where you get to work on so many different types of subsystems, and you can see some of them in this picture. So yeah, as I say, it's been a great learning experience, but some of my advice would be for the younger people would be if you find a company you want to work for, just persevere. It took me about 6 months to get my job at Reaction Engines, and I've enjoyed every minute of it. Right, so Reaction Engines started with these guys. It's Alan Bond, Richard Varvel, and John Scott. So John Scott sadly passed away, but what I can say is Alan and Richard are like the most knowledgeable and nicest people you could ever wish to work with. So they're my engineering heroes. And there's, I guess, Alan Bond, there's some pretty good stories about him when he was a boy. There's one when he said he blew his mum's kitchen windows when he was making rocket fuel in his mum's oven. And another one, there's a newspaper article of him owning rocket fuel that he'd made himself, and the police were threatening to fine him like £100 a day, which is a colossal amount that many years ago. So Reaction Engines was founded to carry on the work of Hotel, which I'll get to later. But first, so why would you want an air-breathing rocket engine? Well, one of the big reasons is you could save mass. So liquid oxygen is pretty heavy. So in a typical launcher, so Saturn V, 85% of that mass is in propellant, and most of that propellant mass is in the oxidizer. So if you can use the atmosphere on your way to space, that offers a great possibility of saving mass. And put that into context from my calculations. So a Saturn V has nearly 2,000 tons of liquid oxygen on board, which is a colossal amount. So if that can be turned into payload, you could be on for a winner. So just to say, there are other forms of high-speed flight, but I guess importantly, not all of them can start from zero. So scramjets and ramjets can't start from zero, and that's where the Sabre comes in. It can. So it's got the efficiency towards a turbojet, but the power of a rocket. So although you might be able to save all that weight, you've now got to exchange that weight for more complicated hardware. So from tanks to heat exchangers and pipe work to turbo pumps and things like that. So this is where Reaction Engines is an expert at developing ultra-lightweight heat exchangers. So if you go on their website, you'll be able to see about HTX, which is a hot test experiment heat exchanger, and there's a bit more detail there, but this is the test rig. So the hot air comes in on the right hand side, comes in diagonal, spills out radially into the heat exchanger, then out the front, which is on the left hand side. Okay. So the history of air-breathing rocket engines, they go back to the 1950s and 60s, and it started with the LACE engine. So the critical point about the LACE engine is it liquefies the air, whereas we'll see later the Sabre doesn't. So I guess one of the interesting things is to liquefy the air, you need more liquid hydrogen to liquefy it than you can burn in the combustion chamber. So you end up wasting a lot of liquid hydrogen. So that's not a good thing. There's also no pre-burners, which we'll come to later. So there's no, in this sort of simple diagram, which I've stole from Bob Parkinson, we'll talk about later. He is also involved with the HOTL project. There's no pre-burner, so you can't start from zero. And there is something magical in this engine. It's the oxygen separator. So I'm not sure anyone in the world knows how exactly that works or how it could be used to function in such an engine. But who knows what the Americans have been up to since. And anyway, this engine is designed to go into something called the aerospace plane, which is their single orbit system, single aircraft to orbits, instead of throwing away rockets like we do at the moment. Right, so if you fast forward 20 years, we come to the HOTL project. So I'm just going to get a drink. Right, and the HOTL project was a project by Rolls-Royce and BAE Systems, and this is where Alan Bond comes in. So he's designed like the RB545 engine, and you can see the patent for it. The patent drawing's pretty difficult to go through, so I won't be going through that, but you can see the illustration of the space plane. And then this sort of ran from the 80s and finished in 1989 when the funding ran out. And so Bob Parkinson, who I've been getting the diagrams from, Alan, Richard, and John Scott all worked on this. And one of the big problems they faced was the icing up of the heat exchangers. So I guess they hoped that wouldn't happen, but unfortunately it did, and that blocks the airflow from coming in. So once that happens, the whole thing falls apart. And the other thing to note is that not liquefying the air means you can save on the amount of hydrogen needed, and by about half. So there's a big saving there that comes in. Right. So this is a little bit easier to understand this diagram. So it's again from Bob Parkinson. So it's quite hard to find lots of things out about HOTL, partly because it's so long ago, and partly because it's shrouded in secrecy. So some of the patents are still non-public, but I guess everything I'm showing is in the public domain. So if we can sort of, one way to think about this, or the easy way to think about it, is to remember it's a dual mode engine. So you've got air is one mode, air breathing's one mode, and then rocket mode's the other mode, which is this LOX tank. And that gets activated when you're traveling to outer space and you're starting running out of air. So that's when that comes in. But to understand the engine, it's almost easier to ignore that for the moment and look through the diagram where the air comes in at the bottom. It gets compressed. Some of that air goes to the pre-burner, and some of it goes to the combustion chamber. And with the liquid hydrogen, some of that goes into the pre-cooler. Well, all of it goes into the pre-cooler through a heat exchanger, and then turns the turbo machinery and then into the pre-burner itself. And as that ramps up in heat, that then starts driving the machinery. And you can see some of that hot hydrogen, getting mixed up with the engines here. The hot hydrogen then can run the air compressor. And the thing to note is that the pre-burner runs fuel rich, so it gets heated in the pre-burner, and then it gets ignited again, the fuel that's not been burnt in the combustion chamber. So like the inventive steps then, and I'm sure there's more than these two, but two of them is from the LACE engine, you've now got a massive temperature delta. So in like thermodynamics, as soon as you've got a big temperature difference, so from the Mach 5 air, which is at 1,000 degrees, to the liquid hydrogen, you can use that to drive machinery. And that's like one of the key things that Alan's recognised, and that comes along in many heat engines, which I've got a diagram of there. The other thing is finding out about pre-burners is kind of difficult to find without showing any reaction engines hardware. It's quite difficult to find any good pictures of it, but this one I found in the bottom right sort of displays it quite well. It's like a shower head of injectors which mix the fuel and oxidizer, and then you can think of it as a generating hot gas stream to work the heat exchangers, to then work the fuel, to then work the pumps, sorry. And pre-burners are pretty common in most rocket engines. So they would normally drive the turbo pumps. So I'll not talk about this one now, but on the bottom left is a simplified Sabre cycle, which these slides will be made available at the end. So it's a good place to try and figure out what's going on in your head. Because even after 7 years, I still struggle. So, all right, so jumping forwards a little bit now, we get to the Sabre 3. So this is probably about 7 years ago when I started. And one key thing to note is Sabre 3 means there's more than one of these types of engines, which is kind of exciting. So you can, if anyone feels brave, they can go away and try and think of better ways of organising a Sabre engine tonight. So you could, for instance, instead of putting all your liquid hydrogen into a pre-burner, you might want to try and divert it into a rocket engine, for instance. But the advantages, or the Sabre cycle from reaction engines comes about for two reasons. One's to get over some of the patent issues, but they also introduce the helium loop. And the helium loop's a good idea on one respect, in that you're avoiding hydrogen embrittlement, which is a big problem. And then you're also avoiding hot air contacting hydrogen, which is explosive. But then you've also, on the other hand, you've got the difficulty of another like loop in the system. Right. So let's talk about some of the challenges. So the state of a typical rocket combustion chamber might want to run at 140 to 200 bar for like the state of the art. And the state of the art turbo compressor, like a Trent 1000, has a 50 to 1 combustion pressure ratio. So you can't stuff the air from a conventional turbo machine into a rocket chamber very easily. Otherwise, you're going to have to run at lower pressures. So one way around this is to have two combustion chambers. So on the left-hand side, you can sort of see at 42 is one combustion chamber, and at 32 is the other combustion chamber, which So you could have one as air breathing mode on the outside, for instance, and one as rocket mode on the inside. And in air breathing mode, you've got an inside out type nozzle arrangement. And then as you're going into outer space, you transition to rocket mode. And I guess one of the neat things about this is you can, as you're going up in altitude, the efficiency of your rocket nozzle changes. So one way to combat that is to have a change in rocket nozzle geometry. So as the higher you go, the bigger nozzles you need, basically. And that solves that problem in one go. And this is actually a patent of Alan Bond and Helen Weber, owned by Reaction Engines. So if you go online and look for Alan Bond patents, you'll find quite a lot of the secrets in there. Right, so some of the other questions you normally get asked is there any other applications? And so again, before my time at Reaction Engines, but there's the LapCat project, which was run with ESA. So you can imagine it as the Sabre engine, but without the rocket mode part. So without the liquid oxygen tanks. And so the headline of this is a Sabre type engine in air breathing mode. Can go to Sydney and back, London to Sydney in something like 4 to 5 hours. And the thing that I like the most about it is it's not a direct flight. You travel over the North Pole, down the Pacific, and then you pop out at the South Pole to get to Australia, which is pretty neat, pretty unusual. Okay, so having worked at some high-tech development projects, you sort of start wondering how should it be done and what's the best way of doing it. And I'm not an Apple fanboy, but Steve Jobs does say a lot of good stuff, and some of it's quite controversial, I guess, to the standard big aerospace type model of how things are run. And I guess it's the obvious one, but hire great people. And the other thing that he says is hire great people that don't need to be great people don't need to be managed. You just let them get on with it. And that was really quite what what Reaction Engines was like when I joined. So you just got on with the job, which was brilliant. The other thing is you can change people's knowledge, but not necessarily their attitude. So it's more important to get people with a great attitude because they'll go and learn what they need to know anyway, than to have people that are difficult to work with. Because at the end of the day, no one knows everything. We've all got to work as a team. And this is the other thing, a diverse team. So that's sort of my quote, in that when we looked for people, it was always important to have people with different backgrounds, because if we had everyone that was like myself, they would have had no manufacturing experience and we would never have been able to build anything. So it creates a culture where you can learn a lot from each other, which is really enjoyable to be in. So this guy might be a little bit less familiar, but he's Warren Buffett, and he's one of the richest people in the world. When I checked earlier, I think he's number 7. But this is a great one for everyone, really. It says invest in yourself. So the best investment you can do is investing in yourself, and that might be training. Well, I guess it is training, mainly in training is what he's talking about. But I think this is also true for a company. So you should invest your key technology. You should be investing to do that yourself and not outsourcing it, because effectively you're ending up paying for someone else to develop your technology. So that's what you should avoid. But you've got to be realistic. At the end of the day, you do have a finite amount of people in your company, and you can't necessarily do everything. So you try to outsource the least technical stuff, or the least IP stuff on that account. And the other one is culture, and culture is really hard to explain or put a finger on what it actually is. And the reason I've got this picture, so this is a picture of an engine that I worked on, and I made a big mistake, a costly mistake, and when that went wrong, I think everybody felt personally responsible. And instead of like running through NCRs and process control and trying to put in a procedure to stop that happening again, in development, if you'd have gone the procedural route, you'd have spent more money trying to fix a problem than actually fixing the problem itself. So it was a humbling experience for me to make such a big mistake. And someone might ask, but it was I made some mistakes in the machining of a rocket nozzle. So when that happened, the production director said, if you haven't made a mistake, you haven't done anything. So that's very true, and that's sort of embodying the fail fast approach to like what you hear from Jimmy Wales and other tech people. There's one other thing. So when I was looking around at this, I sort of wonder, well, how do other industries do it? And the software industry is, I guess, probably got a different view on it in their development. And they say about individuals and interactions over process and tools. So that's pretty heresy. So like in a big aerospace corporation, it's all about tools and processes. But when you're designing a new engine, you can't go to a manual to look at what to do and what's the heritage and what was done last time. So you need to put your people ahead of your processes. And I should also say, for good reason, in big aerospace, they need to keep everyone safe. It's all about safety, but in development, it's not about safety, it's about developing quickly. Right. And the last one I've got, but it's interesting, I'm sure there's many more, but scale does matter. So thermodynamic engines don't always scale well, and this is one of the first examples of this is James Watt's model Newcomb engine. So no one really remembers Newcomb, but the first sort of steam engine was made by Newcomb, and James Watt's genius was to find out why it didn't work very well when it was scaled down to a model. So he figured that out, added his own sort of condensers and heat exchangers in there, and improved the efficiency dramatically. So scale of an engine is very important, and I'm glad to say reaction engines have got some very, very clever people that look after that. I mean, the other thing is, so thermodynamically, the engines don't always scale well, but also cost. So cost obviously goes up incredibly as the scale gets bigger and bigger and bigger and gets more unmanageable. And I guess following on from that, so quite interestingly, as I say, turbo machinery doesn't always scale well. So this is a Balgi turbine chart. So you get the same thing for a compressor, but depending on the size and the scale and the thermodynamics of the machine, you could, for one instance, be looking at a radial machine, and then the next instance be flipping to an axial machine. So you totally change the architecture of your machine, which I find fascinating, and I didn't expect that, but that's something I've learned whilst being at Reaction Engines. Right, so that's pretty much the end of my presentation. So this will all be made available offline or after the show, but the Free Rocketeers documentary I could highly recommend. So that would be able to tell you more about reaction engines than I can and give you a better overview. I've probably watched it about 5 times. There's quite a few Alan Bond lectures that you can find on YouTube, and the Steve Jobs hiring advice, which is fascinating because it's almost it's sort of in the face of the normal establishment of the way it's sort of done now, I guess, in the big companies. But he's managed to do it in like one of the biggest companies in the world. Okay, I want to thank you and for any questions. Oh, I'd just like to add, if anyone wants to contact me, feel free to email me on the email below, and I'll get back to you.
So first, thank you very much, John.
Yeah, thank you.
Yeah, we'll hear from the Bath and Bristol Young Members panel, and then we'll read out the questions.
Okay. Yeah.
Hi everyone, my name's Oliver Thibod. I'm Vice Chair of the Bath and Bristol Young Members Panel for the IMechE. I just want to thank John for speaking on behalf of the IMechE, and also thanks Nick for organising such a fantastic event. If anyone's interested in getting involved with the local IMechE panel, then if you just do a Google search for IMechE Young Members Bristol and Bath, you'll get all the relevant info on our website, and on there is some contact info. And you can send a message to any one of the committee members, and we'll get you invited to our monthly meetings, which are all held virtually these days. So it's never been easier to get involved. It's great for your professional development and building a network in your local area, and I'd highly encourage it. Thanks.
Awesome. So, John, yeah, thank you very much for speaking. Now, I've heard quite a lot about air-breathing rockets in the media, but I don't think I've ever heard such a comprehensive technical description. So thank you very much for that. It's also great to hear an engineer talk about failure as well. I think, actually, from a personal perspective, we'll look at organising a chain talk around failure in engineering, as it's so important to understand how we can grow from our own mistakes. And obviously, often we can make huge bounds from learning from those errors. I know I certainly have in my career. So in terms of questions, for being a rocket scientist, it seems like an amazing career. Are you able to explain what kind of path an engineer would take in order to become one?
I can say how I got there. So I studied aerospace engineering at university, and then I went to work in a design office for an aerospace company, GKN Aerospace. And then I guess a lot of things are down to perseverance and luck, I suppose, being in the right place at the right time. So I was lucky to be looking for a job when reaction engines were looking for people. And when I'd latched onto them, I guess it was perseverance is one of the big things. So if you find a company you like, persevere with them and try not to take no for an answer, I guess.
Thanks. And the next one is this technology suitable for aerospike type nozzles that work at all altitudes?
Oh, that's a good question. My feeling is, so I'm more of a mechanical hardware type guy that likes to get things made. So I'm not a aerodynamicist. But I think you're right. I think you can have an aerospike type nozzle that works with a Sabre engine. But I wouldn't know about all altitudes, I'm afraid. Yeah, sorry. But if you ask that question to me to my email address, I'll try and answer it as best I can because I'm still in contact with lots of people, so I can answer that. I was also could mention that quite a lot of friends that work at reaction engines are not always from an engineering background. So some of them have studied physics, so it's sort of physics, maths, so any sort of STEM subject to really, to be on like the technical side, that's for sure.
We do have another question. So, actually, it's from Ian Parsons. So, I would, just encouraging people to get involved with the Bath and Bristol Young Members Panel. And their offer, it says the IMechE in the Southwest are offering training in January 21. So if anyone locally to Southwest England, do get involved with the Western Region IMechE and their Young Members Panel in particular. So, thank you very much, John.
Thank you.
Our next speaker, who's speaking on behalf of the Institution of Civil Engineers, is Adam Gates, who'll be speaking on engineering net zero.
Great, thanks, Nick, and thanks to Chain Southwest for inviting me to speak at the event this evening. So as introduced, my name's Adam Gates. As a bit of background to me, I'm a chartered civil engineer with over 15 years' experience in the energy sector, working on major infrastructure projects in renewables, nuclear, and conventional power. My current position is as an associate director for Atkins nuclear and power business, covering the Europe, Middle East, and Africa region. So as you can see from the slide on the screen at the moment, the topic for this presentation is engineering net zero. So engineering net zero is the overarching title that myself and other colleagues in Atkins use to frame our engineering assessments on the UK's net zero challenge. So if I move to the next slide, what do we actually mean by net zero? So for context and a bit of scene setting, the Committee on Climate Change, which is the government advisory body on greenhouse gas emissions and on climate change preparation. So last year, middle of last year, they published their net zero report, which included a new recommended UK emissions target of net zero greenhouse gases by 2050. So the legislation at that time was actually for an 80% reduction on 1990 levels. Shortly after the publication of that report, the government accepted the recommendation and enshrined it into law, which, from my perspective, from a lot of people's views, was a really hugely positive step, and actually made the UK became the first major economy to pass such an emissions law for net zero. But that means that 2050 is a challenging timescale, and there's lots to be done. So why is that net zero target important? Well, I mean, fundamentally, it's an issue that affects all of us, especially in the growing context of the climate change debate, of which you see so much more coverage sort of in the last year, in particular on that particular topic. From an energy and infrastructure industry perspective, the required transition to net zero is truly transformational. But also as consumers, we will have to look at and change our day-to-day behaviours. There's absolutely no doubt about it in order to achieve the target. So it really does affect us all from personal and professional level. From an Atkins perspective, we wanted to add our voice to the debate, primarily because it's the right thing to do, but also because we're a major UK engineering firm, and as one of a small number of firms to work across all aspects of the supply and demand side of the energy system. And in particular, we're looking at this without a particular technology agenda to push or technology axe to grind. So hopefully the assessments that we've undertaken in this area provide a balanced view of the various aspects. And what we've aimed to do in our work is to move the discussion on from modelling of the system, which is what authoritative bodies like the CCC have looked at extensively, and moving that modelling into a discussion on and considerations on the practical engineering implementation. So basically the net zero starting gun has already been fired, and in the context of the massive scale of the challenge ahead, 30 years really isn't that long a time. So there's a lot to look at and to focus on. So just touching briefly on the approach that we've taken. So at the heart of all of this is a systems-based approach. So what we've looked to do from the output from the modelling, and I think it's important to note that we have taken the modelling results from others, in this particular instance the CCC, as opposed to actually doing modelling ourselves, because that's just not our area of expertise. There are far more competent bodies than us to look at that. But what we've done is reviewed that and the output for the modelling and the major components in a systems-based approach, identified the interconnections between the components, and then for those components, undertaken an engineering assessment, which looks to consider what the technologies are that are being proposed, to consider whether they're proven and whether they can be deployed at the required rate, and then also to take a view on the technical and commercial risks associated with those technologies, and looking to wrap those up in sort of a general risk framework and to provide some conclusions and recommendations. So the next slides will start to look at some of that in a bit more detail. So hopefully this is clear on the presentation, but what's presented in the diagram on the slide here is a representation of the net zero system itself. I'll touch upon the major components shown here, but I'm going to focus on my particular area of interest, which is the supply side and in particular the power generation aspect. However, that said, at the top of the diagram in the three boxes there represent demand, and they've been split into heat, transport and industry. But in the context of today's, of where we are today, and certainly the trends moving forward, I think that we should also look to explicitly call out data as a box, because that places significant demand on energy resources today, and is growing massively based on our consumption trends. With cloud computing, with streaming services, with all of that those aspects. So I think that is something which would be good to put into the mix. But if we look at the three which are here as of today, transport, well, there's definitely a push for electrification of cars and trains in a significant way, which I think is all known about from most people's understanding. From a heavy goods vehicles aspect, there's a drive towards hydrogen fuel cells, which are certainly not heavily deployed by any means at the moment, but certainly that seems to be the direction of travel, if you'll pardon the pun, for that aspect. But I think there's also the real nettle which needs to be grasped in the aviation and shipping sectors, which for transport are such heavy greenhouse gas emitters, and yet are really quite challenging in terms of what the solutions are for them. But we have different parts of our group who are looking at those and providing some views. So I won't touch upon those further here. In terms of the industrial side, so again, there's a trend towards electrification where possible, but also a view to deploy carbon capture and storage for high emitting processes such as cement manufacture, where there's no alternative readily made at the moment. And then if you look at heat, so that covers process and domestic. Again, there's a balance to be struck between electrification of that aspect, or potentially alternative energy vectors, for example, hydrogen. So you could look at the natural gas boilers in a large number of UK households at the moment, and the potential massive program of works which could be deployed to swap those over to air source heat pumps along with a hybrid hydrogen option. But again, that's something which is to be determined as to what that system, what the makeup of that particular aspect looks like in 2050. And I think actually it's important to note that whilst the system is reflected in the main components here, the final numbers that the bodies like the CCC report on, are just a direction of travel and a proof of concept at the moment. And the one thing I can absolutely guarantee is that by 2050, the final system, hopefully, if we're successful in deploying a net zero energy system, will not come down to the exact numbers which we see here. But as I say, this provides a direction of travel and a general point to consider. So moving on to the supply side, so the circles within this diagram, and I think just a point to note that some of the risks that we've captured or assessed in those are reflected by the green, amber and red circles, either on the technical side or the commercial side. So that's kind of a snapshot of our considerations on those. Left-hand side in the diagram is power generation. You can see there a significant renewables component, and a large amount of that is offshore wind, which I think it's absolutely right to say it's been a huge success story in the UK over the last 20 years, and has been really supported by positive government policy for that industry to allow it to be able to develop to sort of the position where it's at today. So in today's position, there are about 10 gigawatts worth of offshore wind deployed around the UK waters. In 2050, that's potentially going to be looking at something around 75 gigawatts. So how is that going to be achieved? Through larger turbines, through improvements to capacity factors of the turbines themselves, and also moving into deeper waters to access better quality and higher wind speeds, which pushes you towards technology from fixed foundations into floating. So whilst it might seem slightly odd that we've categorised the technical and commercial risks associated with offshore wind in particular as amber, it's really to reflect that move towards the use of floating technology, which isn't yet deployed at scale. So if you look at on the other components on power generation, we've got nuclear, which is technologically understood. The technology has been around for 40 plus years, but commercially it's unbelievably challenging to get the sort of the projects at such scale deployed, as is noted by various challenges in the UK new build programs at the moment. The other two areas there are bioenergy and CCGT. So both of these, if they are going to be classed as low carbon, or in particular for CCGT, will require carbon capture and storage to be deployed alongside them to actually reduce the emissions there, which is why you see the link. On the right-hand side of the system, we've got hydrogen. So at a headline level, in 2050, there are potentially up to a 10-fold increase in hydrogen usage from today's values. So that's about 270 terawatt hours of potential hydrogen use. I think there's a growing acceptance within the industry and beyond that the hydrogen economy will play a role. To what extent it's significant remains to be seen in achieving net zero. But I think it's important to note that hydrogen is an energy vector. So because it's not freely available as a gas without using energy to create it or to separate it, I should say, it's not a direct energy source. And the impacts that have are that overall conversion efficiencies from production through to transport, storage, and use mean that the efficiencies can be significantly lower than one would hope, and so that has an associated cost with it when it comes to its use. And indeed, one of the major hydrogen production processes is steam methane reforming, which inherently produces CO2 as a byproduct. So then you have another link to carbon capture and storage, CCS, as part of that. If we then look at CCS as an individual component, by 2050, there's the potential requirement to capture and store up to 176 megatons of CO2 per year. So context with where we're looking at today, so that's 176 megatons of CO2 annually is 4 times the current global CCS capacity that we have today. So that's a big scale up. But actually, fundamentally, the technology is understood. So the capture technology to transport CO2 and to store it, those individual elements in the CCS chain, we understand and are relatively comfortable with. However, the challenge comes when looking to integrate those components at scale and with a diverse source of emissions. It's just not proven at the moment. And it's something which, particularly on the commercial model side, is a real challenge as to how we're going to unlock the potential for CCS in that regard. In the centre of all of this is system balance. So reflecting on the makeup and components of the system that I've just described there. So the system which has a highly electrified demand side and a large component of intermittent generation requires really, really robust system balancing. And that's going to be achieved through demand-side response, interconnectors, and storage. So demand-side response, it's what the grid operators sort of do on a very very live basis. Today, it's going to become more and more highly complex as we look at this system in 2050. For interconnectors, again, we are plugged into a grid of interconnectors within Europe, and it's not novel technology. But what will be a challenge if over the future decades is that as we and other European countries move towards a low carbon generation sort of approach, we're actually going to find ourselves with experiencing similar climatic conditions. So, for example, solar or wind, there's a good chance that we will be experiencing the same peaks or lulls in demand at the same time. And as a number of firm low carbon generating options such as nuclear or CCGT with CCS, as things start to come offline, and so we have to look to plug in the capacity gap already. Interconnectors might not necessarily end up being the most reliable source for balancing the system. So just a point to note. And then finally, the storage aspect. So this is where I think it's the real challenge that we see from an engineering perspective when you have a system which has high penetration of intermittent energy generating sources. Grid scale storage, at the moment is really only serviced by pumped hydro schemes. So we have Norwick Power Station in Wales, which is the one example in the UK. From a hydrogen perspective, well, that could possibly act as a seasonal, as a store. It could be stored to be drawn upon for seasonal heat demand fluctuations. But when you look at batteries and the current technology and potential for large scale grid storage options, it just doesn't exist. And I think that's a really important thing that some voices within the industry and within government will happily default to. Storage is going to cover us for how we solve this problem and how we can push particular components to a greater extent, and we do struggle from our assessment to completely back that idea. But anyway, that's something to consider further. So if that gives a general overview of the system, I'll move into the next slide, which does a bit more of a deep dive on power generation. And the two pie charts here show on the left-hand side today's electricity generation capacity by technology. Well, in fact, it's 2018 is what was reflected in the numbers there. And on the right-hand side is the 2050 generation mix. So electricity generation headlines for the 2050 system, there's an approximate doubling of the annual generation output of electricity. And in fact, in that generation output, that means a quadrupling of low carbon generation sources, low carbon generation output. And on the peak demand and installed capacity, you're looking at an approximate trebling of the numbers from today's system. So it really is radical change that you're looking at. But one feature of the system, or of the energy mix to note, which again relates to the system balancing point that I made on the previous slide, is the reduced levels of firm power capacity. So you can see that firm power is indicated in both pie charts by the grey line sort of circling some of the segments, and you can see there's quite a significant reduction of firm power, low carbon, in the 2050 pie chart. And what that means is that it's reinforcing the fact that there is high penetration of intermittent generation sources there, which potentially has the risk in terms of system resilience overall. And then if you couple to the intermittent versus power piece, the fact that 60% of the right-hand side 2050 firm power options are dependent on CCS to deliver low carbon generation, then actually, you can see that suddenly the interdependencies within the system start to come into play, and this is where some of the risks start to come to the fore. So as I say, just stepping through the assessment is really started to highlight some things which are interesting to flag to a wider audience. I'm not going to dwell on this slide, which is just a couple of charts to show, well, actually really just what the capacity market, so what the energy markets in the UK, how they treat intermittent sources of electricity. They actually have derating factors to reduce the assumed capacity that's available to the market. So again, it just reflects a practical commercial approach as to sort of the firm power versus intermittent source comparison. But going on to the engineering implementation aspects of the net zero system, and in particular on the power generation side. So this graph hopefully is a fairly clear representation of the scale of the challenge ahead of us. it's estimated that you're going to need about 9 to 12 gigawatts of annual capacity addition in the UK if you were to consider a linear progression, a linear deployment of the net zero aspects. So that's represented by the light blue bars, which are on the from 2020 onwards on this chart. And what's shown from 2020 and earlier are the actual annual capacity additions, which have been added to the grid since the 1960s. So you can see there's clusters of coal stations around the mid to late 60s and early 70s, a spread of nuclear stations across the 70s and early 80s or mid 80s into the 95 for Sizewell C. The dash for gas is reflected in the grey bars from the mid 90s to early 2000s, and then what we see now in terms of the technology drive for renewables, particularly in offshore wind, is represented by the pink bars there. But across that full spectrum of generation deployment, 6 gigawatts is the highest we've achieved across that spectrum, and so you can see that the gap between that and the potential requirements for net zero are significant, and that's even considering a linear deployment. And I can tell you now that in 2020 we will not be adding 9 gigawatts as a minimum to the of bars to the grid. So the challenge is moving to the right. I say hopefully that this image just provides a useful representation of the scale of things. On the next slide, there's a bit more of a deep dive that we've undertaken into individual technologies within the generation build rates. So on the left-hand side, you can see a comparison of what we've calculated to be the required linear deployment rate versus the actual rate of deployment. And so again, I'm happy to take the view that we don't necessarily need to deploy in a linear fashion all of these technologies, but it gives a good comparison just to sense check where we are today, and you can see a mixed picture for the values for the current and required on the left hand side for those individual technologies. But I think it is important to highlight on the right hand side that carbon capture and storage currently has a 0 run rate versus its 6 megatons of carbon capture and storage required rate, and that's not going to creep or jump up anytime soon. There are demonstrator projects which are being developed at the moment, but I think that again looks to highlight the risk of CCS deployed at scale for the net zero system to be successful, which is why on the left hand side the two purple bars against natural gas and nuclear provide one of the mitigation options that you could look at if you were to assume that you wanted to lower your reliance on CCGT with CCS as a firm low power low carbon source. One option is the only option for the firm side is to increase your nuclear deployment. An alternative option would be to increase your renewables, offshore wind, solar, whatever it might be. But again, reflecting what the challenges might be around the risks of system balancing is something which requires careful consideration. But anyway, there's a level of detail to the assessment which hopefully allows some practical decisions to be made in a more informed manner just by what we've been looking at here. And I think on the next slide, it's also important just to note when we look at a system and modelling an optimised system, that also includes a cost element to both build and to operate. And generally, what we see in generating sources today is a consideration around levelized cost of electricity. And that's the term which is used to peg the production values and sort of the potential government support values for offshore wind or for nuclear. Now that LCOE is equivalent to the cost of electricity at the point of generation, and it doesn't allow for a comparison of apples with apples, as it were. And the reason why it doesn't is because it doesn't actually account for balancing costs and system impacts at the point of use. So it's at the point of generation and not at the point of use, which is why we would be really keen to see the discussion around optimized costs for various technologies to be framed around the whole system costing approach, because that, although it's not it can be quite challenging to actually develop those costs for various technologies. I mean, a lot of work has been done around it, and what it does demonstrate, as shown in the diagram or the graph on the right hand side, is that actually where there might be a broad consensus that offshore wind is significantly cheaper than nuclear, for example, if you start to build in some of the costs and the risks associated with each technology, then the costs actually start to at a whole system level start to look a little bit more comparable. And I think that's whilst the graph here is not an exact science, I think it does start to provide that general steer on the debate. So one which we're keen to promote. So I'll finish up with the slide here and just touching upon some of the key conclusions which are listed. I won't go through them all. I mean, our assessment, particularly on the energy supply side, is broadly to say that we think that it's achievable to have a successful net zero system deployed by 2050, but clearly that there is a high risk of failure across a number of those areas. CCS being a critical part of net zero, but also posing the biggest risk, as we've noted there. One of the things which we would like to, or we have proposed to be implemented as part of this process, is what we're calling the energy system architect. So if you look at the system diagram, there are a whole host of stakeholders, both from industry, consumer, from government, a really diverse mix of stakeholders, and trying to get a coordinated approach to understand what the impacts of a decision made in domestic heating might have on energy demand or hydrogen production, for example, is something which at the moment isn't coordinated. And so we would propose that there's an overarching body of some description, we're calling it the energy system architect, to act in that function, to be able to provide that overseeing, coordinating, plan setting approach. We'll be looking to publish some more information on our thoughts on that in the next month or so, but I think it's a really vital conclusion and recommendation for us. The other conclusions there we've touched upon as we've gone through, but I think I'll say in broad terms, there is a significant investment and massive deployment rates that are required to achieve net zero by 2050. And as I mentioned before, there's a fundamental consumer behavioural change that's also going to be required to make this a success. One of the key takeaways for us is that to try and mitigate against the risks that we've identified and that could arise, the best thing that we could do, in our opinion, is to keep all options for technologies open for as long as possible. We see that as an essential step, to be able to help mitigate risks as they evolve throughout the next 30 years. But no, it's a fantastic time to be involved in the energy industry as we see this transition and this transformation start to unfold. And for sure, there's an awful lot of opportunities across the patch here. So if it's an area which you're interested in as sort of engineers at the start of your career, then there's an awful lot of opportunity, and I'd really encourage you to have a look at it. So from my perspective, please feel free to get in contact with me directly or via Chain Southwest. If you want to look at any more information specifically on the net zero work that we've done, then you can access that through the link on the screen here. But yeah, no, that's all I had to say in terms of the presentation content for engineering net zero. Before I move into or go back to Nick and just check on any questions, I just wanted to do a quick plug for ICE Southwest on behalf of the team there. So in particular, the ICE Graduate, Student and Apprentice Committee for Bristol and Bath. So it's a group of students and young engineers, young professionals with civil engineering background in the Bath and Bristol area, and they come together on a regular basis to look at technical talks, for tours, site visits, socials as the current situation allows, and various careers events. So it's a great forum to sort of pool collective minds. And just a date for the Civil's diary is that the AGM is coming up on the 24th of November, and if in particular you'd be interested in joining the committee, then please do, or finding out more about it, but please do email ICE Southwest as the address is on the screen there to find out more. So that's it from me. I'll hand back to Nick for any questions, but thanks very much for your time.
Brilliant. Thanks, Adam. So for one, I'm fascinated by the prospect of floating wind turbines. That's not it seems kind of obvious, but it's not something I'd actually considered before. And it's great to see how these different technologies, such as carbon capture and storage and hydrogen, work together to reduce our environmental impact. It's great to see it sort of in a coherent picture rather than hearing about the individual technologies. So we do have a few questions. And I know you touched on this one a little bit, but what level of battery storage or other storage technology would be required to support the large volume of renewable technologies you talked about in your presentation, and in particular to account for the intermittent nature of the technology? So is there a ratio as to how much storage we might need in terms of against the level of, say, intermittent generation we have?
So I probably can't give you a ratio of that percentage, but what I could probably just draw upon or mention is one interesting fact or consideration against the Hornsea wind farm. So actually, in August last year, there was a drop in connection to the partially commissioned Hornsea offshore wind farm, which was providing approximately 800 megawatts onto the grid at that point, and that happened a few minutes after a CCGT had dropped offline. So give or take around 1.1, 1.2 gigawatts of generation capacity had dropped off the grid in pretty short order. So we did some numbers on the battery storage available today in terms of at that time, I think it may well still be the world's largest lithium battery storage installation, which is at Hornsdale in Australia. And so that has a capacity of 129 megawatt hours, which we calculated was enough to replace Hornsea for less than 10 minutes. So that kind of gives you one of the sort of an indication of scale of the challenge in terms of battery storage. It exists. It has benefits. It has short-term, really localized potential, but at grid scale, which I think is the concern that our assessments have come out with. That's where we're just not convinced that that's the silver bullet by a long way. It's how you can innovatively deploy that to maximize its potential. But grid scale, it's not there.
Okay, and so net zero has a cost. Do you think the customers actually know this and will accept significant energy price hikes? For example, manufacturing hydrogen to displace natural gas. Do you think there will be price hikes, and do customers know this if there are going to be?
Yeah, it's a really good question, and I think it's a real challenge towards the behavioural change aspect of net zero, because you can see a direct cost. For example, if your next car that you're looking to trade your car in, and actually it ends up being an electric vehicle, there isn't a cost associated with that because there's not such an expansive or extensive second-hand network of EVs to be able to draw upon. So potentially you're seeing a cost in that. There'll be a cost to swapping your. It's actually a live conversation I'm having with my wife at the moment on our house refurb plans. Like at the moment, we're doing a whole host of work to extend the house, and we're looking at whether or not we can afford, quite frankly, to include a combined or an air source heat pump as opposed to a brand new conventional natural gas boiler. But that definitely is something which you can see direct impact on your decisions as a consumer. But at a broader level, I think as the legislation was passed by the government last year, Philip Hammond, who was Chancellor at that point, had put out a statement to say that this potentially net zero could potentially cost £1 trillion overall to deploy. Now that's a big number, and clearly there are going to there is an inevitability that consumers will end up footing the bill for a proportion of this cost. Now, how do you get around that? Is it the fact that this is just going to be forced upon consumers to a certain extent with the transition to legislation and transition from high carbon emission sources? Is it going to be an education piece? To say, well, look, actually, there is a bigger picture around this, and this is the reason why we're looking at it. I mean, I do not, for sure, I do not have the straightforward answer to that. But I think the question is absolutely right to point to it being a challenge, to change behavior, to facilitate quicker and faster behavioural changes. As soon as the cost element comes into it, that always becomes a blocker.
Okay, we've got time for one more, and that is: do you consider tidal lagoons as a future part of the energy generation mix? And if they are not, why were they discounted?
So from a personal and from a company Atkins perspective, I do see them as part of the energy mix. And we were actually working for quite some time on the Swansea Tidal Lagoon as an organisation. And I think as the tidal lagoon industry was particularly disappointed not to see that technology included on the last round of contracts for difference, which is the kind of the government subsidy list for energy generation sources. It must have been a couple of years, or a year, 18 months ago now when that was published. So I mean, they can play a part, but again, it comes. If you look at, for example, the nuclear power, especially at large scale, or in fact CCS or hydrogen, whichever technology, they've got to make sense from an investment perspective. If the market's going to be left to its own devices to either build or not build, then there has to be the incentive for them to do so and the business case to build it up, unless there's government support. So we don't want to keep on defaulting to the government needs to up support in particular areas position, because actually that's you can say that about a lot of things, and really there are other challenges which we can move forward without their support. But I think that is a fundamental issue or aspect of the net zero system with regard to affordability and driving some of those projects through, for example, tidal lagoons.
Awesome, thank you very much. And thanks for plugging the IC in the Southwest. So if you are a civil engineer in the Southwest who's just starting out in their career, do please get involved with their activities. Next up, we've got Holly Kimball of REACT and the Ministry of Defence, who'll be talking about reacting to disaster.
Thanks, Nick. Cool. Good evening, everyone. Thanks for having me. I'm here to talk about engineering in the context of operations in a disaster zone. It's not very technical at all, but it's just hopefully an indication of how you can use your technical brain and technical mind to solve challenges in really pressing environments. So my name is Holly Kimball. I'm a Chief Engineer and Specialist Fellow for Directed Energy Weapons. I work in the Ministry of Defence in a branch that's responsible for acquisition for the front line. I'm a chartered mechanical and explosives engineer, so the rocket talk was particularly interesting to me. I'm also a humanitarian disaster responder and a Churchill Fellow, and that I'll come back to later in the talk. So the first part of my talk is about my time in Mozambique responding to Cyclone Idai. And that was a 3-week deployment, which I'll go into now. Before that, however, I need to have a disclaimer as part of this presentation, because my team is no longer called Team Rubicon. We're now REACT Disaster Response. I've been given special dispensation not to have to Photoshop every single photo in this presentation. So everywhere you see Team Rubicon, please now read REACT. Our website is just in that hexagon down there. It's a disaster response charity based in the UK, predominantly based on the military way of life, with military veterans and blue light services making up the majority of our population. But we're also full of kick-ass civilians from all other walks of life. Before COVID, we had over 600 trained volunteers in the UK, but our forces have been enormously boosted during this time. So we have more than 4,000 veterans working alongside us at the moment on COVID operations. And I'm really lucky. The MOD is a super supportive organisation, and I'm able to use some of my paid days to support volunteering. And so this deployment I'm talking about I was fully paid to go and be a part of. So the context of the talk for this evening is Cyclone Idai, which struck Mozambique, Malawi and Zimbabwe in March 2019. You'll definitely have heard of it. It killed over 800 people and was on the news for a long time. It hit closer to home though, because the city of Beira in Mozambique is actually twinned with Bristol. And so I heard about it through multiple channels, partly due to the twinning organisation. Idai made landfall just south of the city of Beira. Beira is where that pink heart is on the right-hand side image. But the landfall had been preceded by heavy rain for weeks, and so the waterways were already completely clogged, and the cyclone pushed it completely over the edge. The water was above 2 meters deep for more than 2 or 3 weeks in lots of different places, so it's actually beyond imagination how much water that is. Team Rubicon, as was given permission to respond 3 weeks after the cyclone. We're not allowed to operate near water for very many reasons, including safety. So floodwater was still over much of the countryside, but the areas we visited as part of our operation were, as you can see from the images, waterlogged but not flooded. The UN established an emergency operations centre at Beira Airport, so that's where I spent a lot of my time. And another key point for context is communication had been lost between regional and local government. So that heart is a very, very zoomed out image because Mozambique is huge. But actually there was almost no communications either. So we relied on sat phones essentially to keep in touch with our people on the ground. And the government had pretty much lost control of the area. So the team, this is my strike team, which is what we call when we deploy. I was the strike team leader for 21 days. It was my first deployment, and it was an absolutely incredible opportunity as an engineer to go and lead a team this diverse. We had some wonderful various backgrounds in this team. We've got a physics teacher stood next to me, Mike just up the stairs. Steph is an engineer for OpenReach. AJ is a tree surgeon, former army soldier. Keith was a former director of nursing and IT for the NHS. And Mike on the top step was a former detective constable for Avon and Somerset Police. And we had some challenges to solve while we were there. As I mentioned, I spent quite a lot of time working in and around the UN Emergency Operations Centre, but we also spent a lot of time out on the ground. We conducted multi-sector needs assessments, which I'll talk about a bit more, and we also established a forward logistics base and airstrip to provide aid for 62,000 people, more than 62,000 people, with lots of engineering challenges to solve to achieve that. We conducted logistic assessments to see whether or not we could reinstate bridges and ferries to allow us to cross the rivers. And we also conducted population assessments. As I mentioned, the government wasn't able to easily maintain control and communication with its people. So moving on to the operational challenges, and this is kind of where the engineering piece meets humanity and being a humanitarian. There were loads of problems to solve, and being an engineer in that environment, it was an amazing opportunity to kick into a gear that you don't often get to use in everyday life. So overcoming some of the shock from the devastation was an immediate challenge, not something that you can solve. So it's not a problem that can be fixed, can be tackled in one go. So sort of learning to see your place in that disaster and see the bits that you can help with. As it says on the slide, the scenes from the helicopters were just almost completely unbearable, and it was devastating every day that I got into a helicopter to be able to see from the air just how bad the situation was, because it's much worse when you can see, the further you can see, the worse it gets. Another operational challenge, and something that I often talk to engineers about, is language and cultural norms, and our ability as technical folk at translating from very, very deep technical jargon into a language that lay people can understand. And so that is a skill that can be used in so many different ways. I am a linguist, so I was able to use my Spanish skills as to communicate with the Mozambicans who speak Portuguese. But actually other members of my team were able to overcome some of the challenges of not being able to speak the same language just by understanding the context of the situation. Lots of it becomes clear if you open your mind to what would I be saying in this circumstance. It's hard to believe, but actually in that circumstance it served us very well. Cultural norms was a really interesting challenge. Needing permission to act when you're seeing such devastation in front of you was certainly a big challenge. We had to get permission from both elders and local government and landowners, in fact, from both sides of a river to be able to reinstate a chain ferry, when actually everything in me was crying out that of course it was the right thing to do, so we should just get on and do it. So that was an interesting challenge there. The infrastructure destruction was genuinely unbelievable. There were very few roads intact. Bridges were completely washed out. The road, which should have taken an hour and a half to drive from Beira to the town of Buzi, where I was staying for the operation, should have taken an hour and a half, 2 hours. It was a 14-hour journey at this point because the convoys that were able to get through had to take such a winding route through the countryside. So we relied very heavily on helicopters to give us taxi rides through from one area to another, but also to transport huge heavy loads of aid because we weren't able to transport most of those by road at first. When we arrived, there were so when Team Rubicon arrived and I walked into the EOC, the Emergency Operations Centre, there was an alarming lack of mapping available for the area, and the pilots were all using grid references and coordinates to coordinate their trips, their journeys. But actually, the people on the ground needed to understand that this is a village with a name of, has a certain name. And there wasn't any way of translating between I need to go to this village called Munamikwa with this is the grid reference for that village. And so one of the things that I did when I arrived was ask the mapping cell to produce us an overlay. And so the map at the bottom is what you see. This is the first map that was produced of the region that had, off the bottom of the map, it actually has all the GPS coordinates for each of these places with a dot on the map. And I mentioned that we undertook the population assessments. We had to find our way between remote locations south of the river that you can see on that map. There was no command and control from central government, so we had to fly to the south side of the river and then find overland transport, hiring local drivers with 4x4s that were still working to take us to regional government hubs to try and establish what the population was. There were only paper records, and so our team produced digitized records for the population using the IT that we took with us, and fed that back to the government. So this is how we ended up with an assessment of 62,000 people as a population below that river. So you can see the red winding line, and then it goes on into a river towards the sea. That the population of that area was 62,000 people, and all of them needed help. It was a real challenge that the humanitarian organisations don't really work together very well. That was a bit of a surprise. It seemed a bit disappointing, to be honest, but the organisation I work for is very, very small, and with lots of former military folk, we tend to break down barriers that don't need to be there. And so I'd established a WhatsApp group within the first day, bringing together the 8 aid organisations that I needed to work with to get logistics south of that river to help the people there. So here's a set of pictures to describe the journey to reaching this establishment of Busy South logistics base. So south of the river, as I mentioned a bunch of times, 62,000 people all needing food, shelter, safe drinking water, cooking equipment, and a variety of other pieces of aid. My team did an assessment of the town of Busy to find a suitable location for so much aid. And so that was a practical use of engineering, working out what volume we needed, how much space did we need, what real estate, what access would we need, what vehicles would we be driving, how would we get there? And the answer was, in the early days, absolutely air was the only way. But you can't use helicopters that only transport 8 tons if you need to be transporting hundreds and hundreds of tons of equipment. And so we needed to set up an airbase to achieve that. And so you can see on the left, it's a very, very simple airstrip, but when you're close down, you can see the feat of clearing all that grass and making sure that there weren't any massive potholes to rip off the subframe of the aircraft as it lands. Top center, you can see the cleared out warehouse as we arrived. That was completely full of mud, more than a foot deep in places, and full of bits of furniture that were floated around during the flooding. Top right, you can see the team unloading the aircraft. That was the first one that arrived. And shortly before that photo, you can see bottom left, that's on arrival. Almost the whole village turned up to help us unload the aid. And there was a huge celebration because it was just such a feat for us to work together to achieve that moment. And then just a couple more photos gratuitously of all the stuff that we stacked up, ready for distribution. So this next slide is showing the logistic assessment and the aid distribution itself. Our mission when we first were sent out was a water mission. So we expected to go and assess wells to see if the water quality was high enough for human consumption. So we went around testing water. What happened very shortly after we arrived was that the kit that we took with us was banned from Mozambique. So we took with us thousands of sachets that look very much like large sugar sachets, about the size of a ketchup, the kind of ketchup pack that you tear open. Those look like sugar. And in fact, when we did the calculations, if a child had eaten one of those, they would almost certainly have died because of the chemicals that were inside. So rightly, the Mozambican government banned it because we were absolutely not able to guarantee that we were going to safely distribute them. So we moved on to a different type of mission, which is what you saw on the slide before with the yellow water containers. We were working with Oxfam to hand out these incredible cubes that are able to filter water safely and last for almost a year. So a really, really good piece of kit. We still carried on with the well assessments, though, looking at whether the water was dangerous or safe to drink, and brought in some other charities to help us make the safe assessments. In the top there, you can see a chain ferry that had come off of its chain, and we reinstated that chain and that ferry after lots of negotiation with the local government, the landowners. And you can see the team carrying diesel across down towards some boats. That was us getting our ability to keep the trucks running. There was no fuel supply south of the river because that had been completely destroyed. So that was a limiting factor that we had to overcome. At the bottom of the slide, you can see one particular day. You can see AJ and myself there, pretty chuffed to have all of this aid being tucked into a Russian helicopter that's able to carry 8 tons. That's 8 tons of both people and aid, and so we had to be honest about our weights when we were loading up. And when we did all the calculations, I realised we had 250 kilos spare for food, and so I went and negotiated quite vigorously with World Food Programme to get that 250 kilos of food on the flight with us, which doesn't go far, but it's certainly better than nothing, better than space and capacity. So an overview of some of the challenges that we overcame. That top left picture, this operation, this deployment was my first experience in my life of water poverty. I'm a traveller, I've travelled for years, but I've never been required to walk 12 minutes each way to a well, carry the water back. If you're unbalanced with a load, carrying it on your head is actually much better. So that wasn't me messing around or posing for a photo. If I was carrying two, I'd have carried them down by my sides, but that is how I transported the 10 kilos of water. We then had to filter that water through a life straw. That took 20 minutes at least. We then had to chlorinate the water, and that took another hour. So we had to wait that length of time, 12 minutes walk each way, 20 minutes to filter the water, plus an hour before we could have a single drop to drink. That experience was mind-blowing. We had a team of 6. At first, there were only 4 of us. And when we were told we were getting an extra 2 people, when I was going to get 2 people out of my team, we sat down and worked out the maths of whether it was worth it because of how much extra walking we'd have to do back and forth to the well. It's something I've never experienced before. The food that we were eating, you can see it bottom left, that's partly the reason we needed so much water. That is dried rations, which was not a good solution to a water poor environment, having to carry extra water back and forth so we can make up this overly bulky and lacking in nutritious meal. The middle, right and bottom, overcoming challenges of not having tweezers for 3 weeks, plucking my eyebrows with a multi-tool. That worked pretty well. At the bottom, you can see Keith and Mike doing some water admin back at base. This place is called Casa Snake because it was home to us, but also to some friendly black mambas, some of the most deadly snakes in the world. They did come into the house, and we found them numerous times, including in one of the Mike's backpacks as we walked out of the house, which was an exciting moment in all of our lives. And so this is the final slide for this section. Just a summary of the experience. It was not all bad. It was amazing. It was incredible to be working with the team, solving loads of challenges, operating at a pace that just does not happen in everyday life. The bonds that you form with people, both the people that we were helping, but the team that I was with was just absolutely incredible. Getting to play around with helicopters was quite fun some of the time, but the pilots are nutters, so they know the limits of their aircraft. You have to trust them, but they don't half like to make us scream in the back. And yeah, we had a pet chameleon for a while, so he's pretty cute. So the next quick session that I just wanted to run through was a project that I am undertaking as an engineer, part of a Churchill Fellowship, which I'll talk about in a second. It's called The Wandering Engineer, and I have a website and a blog set up for this topic. So I was awarded a Churchill Fellowship in 2019, and Winston Churchill Memorial Trust, WCMT, award up to 150 fellowships every year to British citizens, British residents, people in the UK from all walks of life and all ages and backgrounds to run a project of their choice. The topics that are supported are really broad, but STEM falls massively across that spectrum of projects that they'll allow you to run. So you propose a project and they will potentially fund you to go and travel. That's the premise of this is traveling to learn and returning to inspire. And so my project, which I was really passionate about, particularly after my time in Mozambique, was to inspire children to see themselves as STEM professionals in the future. So it upsets me more than anything when I hear someone say engineering isn't for me, or I don't have an engineering brain. Those two things really upset me, because I think it's just a case of not understanding the breadth of what it means to be an engineering person, or an engineer, or a technical person, a scientist, a mathematician, any of those things. There's such a breadth of of topics that covers. And I really wanted to find a way of inspiring some kids to look at that and go, okay, maybe it is for me after all. And so what I did was I spent 7 weeks in Africa. I went to Kenya and Tanzania, and I visited 8 different projects. And I've created a website, and I'm still working on it. So there's bits and pieces coming up. There'll be some lessons for schools added to the site. So this is just a screenshot. But the main focus of it was, as I just mentioned, about the people. There is no one thing that makes an engineer. And so I tried to bring this to life a little bit with interviewing everybody that I met, finding out some interesting facts about them, and trying to highlight that in these blog posts and on these pages. So each of the interviews I did has a separate page. So the blog is fully up and running. There's 20 different posts. You can see every day, everywhere that I went, all of the projects that I went to visit. There's project pages that talk about what each of the projects do and how they use engineering and technology to change the world, change the lives of people. So they're all humanitarian focused, all non-government organisations trying to do good work and using science and technology to do that. So the 3 that I've got at the bottom there, those logos, Popo is the reason that I went. It's the whole reason for all of this. Years ago, I found out that there's an organisation training rats to detect landmines. It's actually become a topic in the news very recently because Magawa got a medal. So this organisation has, since 2007, I think, been in Morogoro in Tanzania, where I went to see them. They have the headquarters and they train rats. And I got to meet some of these rats that detect TNT, so they can look for buried landmines. Because of my background as an explosives engineer, I actually was asked to give a lecture. So I created a talk on how I thought the mechanism for detection worked. A piece of work I did when I went back to uni to study explosives was on novel detection methods of buried IEDs. So it was a real life dream of mine to go and engage with this project and to talk to them about the explosive chemistry behind it. So this was this was fantastic. And I got to do this for free because it was part of this fellowship. So I just wanted to make sure that you guys know and that loads of people, as many people as possible, hear about this fellowship because it's just such a fantastic opportunity. Off-Grid Box, they create ISO container solutions, packed up ISO containers that contain solar panels. When you fabricate it in situ, those solar panels have generate enough electricity to pump clean water from miles away, if necessary, filter it through a filtration system, which is absolutely fantastic, great technology. And they can also charge up power packs, and those power packs can be used to put lights in people's homes. One of the most limiting factors that stops children in these developing areas, in these very poor areas, from learning and from doing well at school is a lack of electricity. So when it gets dark at 6 p.m, because it's 12 hours of daylight all throughout the year, because they don't have seasonal variation in lots of Africa, this light is the key to everything. They can study at night when they get home after school, and this is going to be changing lives and allowing more people to study more subjects to allow them to use their brains collectively to solve more problems. So I think it's just very exciting. Burn create stoves which really revolutionize cooking in sub-Saharan Africa. They use 30% at least less fuel and create a very clean flame, which means that they're going to have so much less pollution coming out of the houses, many fewer lung issues and lung complaints, and also burning less wood, which is, again, a really important issue, especially in sub-Saharan Africa, where we can't afford to be losing any more trees. So yeah, those are just 3. There's 5 more. It'd be great if you could check out the website. And my final slide is just a summary. So the Winston Churchill Memorial Trust, they're the ones who are putting on this incredible opportunity. So please go check them out. If you've got an idea for a project, they're the people to take it to. So you have to come up with your own project idea, but the application process is very simple. And as long as you're over 18, I think they're able to fund you for 4 to 8 weeks of travel in up to 2 different continents. So if you're interested, it's a great opportunity. Cool, thank you very much.
Thanks, Holly. It's pretty incredible how much you achieved in those 3 weeks in Mozambique, and it must have been such a rewarding and valuable experience. I think it's really great to show how we as engineers can use our skills to help people all over the world, particularly in austere environments. I, for one, will admit that when I was young, I didn't consider myself to have an engineering brain, and it was stories like the ones you're trying to champion that showed that you can use engineering in particular to help people, and that in particular is what made me want to become an engineer. Yeah, you do have a couple of questions. So, Holly, totally amazing. What was the hardest challenge, and are you planning on going on any more tours?
So this is a tough one. I'll do the second question first. As a disaster responder, it's a really, really odd feeling because you absolutely can't wish ill on anybody. But I want to be there if the worst happens. And so, yeah, if there are any disasters, I stand ready and looking forward to it in the most respectful way possible. It feels like an amazing opportunity to be able to help and get out there and practically apply my skills. So I've been on a couple of COVID deployments during this time, but the international large-scale disasters are really where you can see the difference that one individual can make. Like the approach that I took in the EOC was quite noticeably different to a lot of people. So being able to have that, just bring that different viewpoint was amazing. I felt very lucky to be part of a small team. The hardest challenge, I think it was probably just seeing that level of suffering, and having a team around me and being part of the organisation, and the way that we look out for each other is really important. So at the end of each day, we would kind of have a heart-to-heart. So we'd sit at Casa Snake and eat our horrible dinner, and sit there kind of just running through some of the difficult stuff we'd come up against. I think that was the hardest challenge, was just how rubbish it was, how difficult it was, being the first people to arrive in a village who hadn't seen any aid workers, hadn't seen anyone from the outside for 3 weeks. And I had to be the one to ask how many people had died in that village. I think, yeah, that was it was one of the hardest things I've done in my life. But walking away from it after 3 weeks, it was certainly the best thing that I've done with my time.
Yeah, well, you certainly achieved a huge amount, so it's certainly, you know that you did your best to help those people. The other question is, who initiates the disaster mobilization? So who actually mobilizes the REACT team?
So there's pretty specific rules about this. When a disaster strikes, an organisation such as mine can send up to 4 people for up to 4 days to go and have a look on the ground and see what's what. After that point, you absolutely need permission from the nation that you're going to, from their government, to say whether you're allowed to stay or not. And so sometimes we'll go and assess a disaster. We'll set up, as part of the international response, there's a website that you can go and pitch and say, hey, these are the skills my team can bring. Do you want us or not? Sometimes you get turned away. Sometimes it'll be political reasons. Sometimes it'll be because you're British, potentially. I've not personally experienced it, but I understand that that's sort of how it works. You're able to say, do you want us, yes or no? But you have to be able to say, this is the capabilities of the organisation. So it's a two-way thing. We can turn up, help with the assessment on the ground, but only for a very limited period. And then we build good links with lots of nations around the world, so that in the event of a disaster, we're on their list.
Awesome. It's good to get an understanding of quite how that process works. I'd not considered that it would be like that. The last comment is that if you are interested in other scholarships, as the Winston Churchill Memorial Trust, the IMechE also gives out around £800,000 each year in IMechE scholarships and awards. And the Western region of the IMechE are very happy to support applications if you guys are interested. So we're going to have let's call it a 10-minute break. So we'll be back at 19:30, where we'll be hearing from Alex of Gravity Industries. See you guys in about 10 minutes. Welcome back, everyone. That is now 19:30. And really, without further ado, here is Alex Wilson of Gravity Industries. Take it away, Alex.
Hey, hello everyone. Hope you're still kind of enjoying the evening. This is definitely a strange way to present for me. Normally it's kind of stages and an audience where you get some feedback, whereas this is sitting at home, nice and comfy with a cup of tea and an armchair in a dimly lit room. It's great. I love it. And also there's no feedback, so I have no idea whether you're kind of enjoying this or not. So I'm just going to assume that everyone's laughing away and enjoying all of these videos. So this is a little story about how we've kind of reimagined human flight at Gravity. Now I realise that no one can see me, so I thought I'd slip in this little slide, a selfie, so that everyone knows what I look like and what my bedroom looks like and my dirty laundry on the door. I didn't see that before. Oops. So this is a story of how someone as normal as me learned to do something like this. Which to me looks a little bit insane anyway. So the story all starts with this guy. This is Richard Browning. He's the main founder and inventor of this suit. And he had this hunch that the human mind and body is such an amazing machine. The fact that we can run over kind of uneven terrain, climb things, I mean, all sorts of stuff, just by training our bodies to do that, that surely we'd be able to fly. I mean, birds aren't that smart, surely. All you kind of need is a little bit more thrust. So, I mean, here's an example of a friend of ours out in America who can demonstrate what the human mind and body can do. I mean, rather him than me. But yeah, it just proves how amazing the brain is at balancing, I guess. So yeah, we need a little bit more thrust. So Richard found these. Now, a big part of this journey is about kind of learning by taking tiny little steps. You might have noticed that instead of a fuel bladder, we've got a mop bucket. We don't use mop buckets anymore. And what you can see strapped to his arm is just a really small micro jet engine, the same kind of thing you'd see on any jet aircraft, I guess. So if one of them seems to work, and this is assuming that kind of all of the original theories of why this would never work have been disproved, and I'll jump back in on that in a sec, but if one of them seems to work, I guess the next logical step is to try two. And we definitely damaged a little bit of crash on this one. And the real hero is the lady doing gardening in the background, which you might just about be able to see. You can see as he's holding his arms out there in front of him. The amount of power is quite insane for these innocent little biscuit tin sized devices. They each put out about 22 kilos of thrust. They're spinning at about 120,000 RPM, which is about 2,000 times a second. And the exhaust gas is coming out at about 750 degrees C. So, I mean, it's not the most natural thing to think I want to strap one of these to my arm or both arms or wherever else. But all the theories that with that kind of huge amount of gyroscopic precession that it would just rip your arm off, or that the heat's just going to be unmanageable, or I don't know, it'd just be a wild force that would rip your arm off. They were all kind of disproved by just giving it a go, gingerly, safely, as doesn't look amazingly safe, but it was done pretty safely, and it's just like a spongy push, really. It's just like a fire hose of water on your arms. So 2 works. So I guess the next logical step is 4. So now we're starting to get about moon-like gravity. And this is starting to get kind of quite promising. You can see it's drifting down slower. So where do you go from 4? Obviously you go to 6. Now this admittedly was a bit silly even at the time. The amount of force there is, I guess it's 60 kilos on each arm. So about 120, 130 kilos total, just balancing on your arm. That was nuts. That was a terrible idea. Now, where else can you put them? So when we're kind of moving around normal day-to-day life, we use our legs most of the time. So surely legs is a good option. And I hope you're kind of enjoying the jet noise. It's probably quite loud coming through, I'm sure. I've got the owner who's helped organise a lot of this on WhatsApp here telling me that it sounds a little bit loud on the jet noise, but I guess it's really loud in person, so it's quite an accurate reflection. Now, if you noticed on that, he was swinging around on a tether. Now, that was a nice idea, But in practice, it was a bit like trying to learn to ride a bike with stabilizers. It's great to a point. It means you don't fall over, which is nice, especially on concrete. But it creates this extra vector that's really hard to deal with, and it's really hard to learn to balance without tugging away on you. Now, you've noticed that we've put them on our legs. Now, this worked pretty well, and we made a lot more progress like this. Looks a little bit silly. But we're getting there. Look at the dust that's being kicked up there. That's painful to look at now. I'll skip through this one as well. This is with 2 on each arm, 1 on each leg again, sorry. And progress is looking really good. And this journey was we never set out to try and build an Ironman suit, but it's quite uncanny how similar that footage looks to some scenes in the original Iron Man film. Now, this next slide is kind of where, this next video, I guess, is where the whole journey turned from just a group of mad people in a farmyard to, oh my God, this might actually work. This is the first 6-second wobbly-legged flight. Which you can kind of tell he's pretty delighted with. So from there, where do you go? We moved those 2 leg engines, which were a pretty bad idea now that we're looking back on it, up to a single rear engine that lives in a backpack on the back where your fuel's stored and all your electronics are stored. And we kind of iterated and iterated. I'll skip the evolution story of how we got to this bit now. And this is a video now of kind of all of the events that we did in the preceding year and a half, I guess. So I'll let this video play out. So yeah, I'm assuming you're all going to be clapping away. I'll give myself a round of applause. This is a nice little break. Now, that was all Richard flying, and up until kind of maybe a year and a half ago, it was only Richard who could fly, and we thought maybe that's because he's some superhuman athlete. I mean, he was an ultramarathon runner, ex-Royal Marines Reserves, and kind of all-round calisthenics buff as well. So we had to try other people, I guess. We had to see if anyone else could fly. Now, meet Ryan. Ryan's the second in the UK at tumbling and gymnastics. Yeah, that's 3 backflips right at the end, which is pretty nuts. Now, surely if anyone's going to be able to do it, it'll be Ryan, because he's got arms like an ox and an amazing amount of balance and control skills. And of course, I think this is his 3rd go. And by this point, we've taken him off the tether, the training tether, because it was just like, clearly didn't need it. Turns out gymnasts, which have been trained from an early age to kind of mimic body reactions, I guess, are really good at absorbing information and just doing exactly what you tell them to do. But my first attempts were a little bit less promising. I wasn't taken off the tether for a while, and there's a lot more swinging around. And what you can almost see in the back is my colleague Lee pulling on the safety tether, pulling me up just so I got a bit of airtime. I was not ready for the amount of thrust. And I mean, you can kind of see from there, my arms are nowhere near like Ryan's. So how do we solve the strength problem? So we started in the same kind of manner as we started with the first jet engine strapped to the arm. We went back to basics, went back to the early arm mounts, and we started hacking together random prototypes of things we thought might help. So when you're trying to hover, you're actually holding the arm engines out to the side. So if you need a little bit of force to hold them out, why not use flexible tent poles attached to the top of the backpack and zip tied in place and drilled in place to the arm mounts? Didn't really work. We tried crutches. It kind of worked, but this was kind of similar to learning to run but with your legs splinted. You need a lot of that fine control. You need to be able to move your elbows even a tiny, tiny amount. And then we had a little bit of a brainwave, and all of these discoveries seem really obvious in hindsight, but at the time you kind of feel like you're stabbing around in the dark. Now this is the first set of arm mounts, fully 3D printed in aluminium, and as you can see, it's perfectly symmetrical. It's a lovely carpet Richard's got there as well. It's perfectly symmetrical out of the arm, and it's the same in kind of the other plane. So all of the thrust is going straight up your arm. Now, you control flight by moving your arms around and vectoring that thrust. So if you're lifting your arms out to the side, you're taking the full weight. So you're taking 5 or 6 kilos of weight up to the side. And after a while, that does take its toll on your shoulders. So how about we use some of that huge amount of thrust that we've got on our bodies just to hold the engines in the right place? And it now seems really obvious. But I did a very, very rough calculation on a post-it note. Here is that post-it note. Did a little bit of a force diagram. Worked out roughly the angle the engines want to be to hold your arm in the right place. I wonder if you can read those numbers. Probably wrong anyway. And we did a very first prototype. You can see on his arm, on his left arm, that the top engine is a little bit closer to his arm than the bottom one. So that's pushing his arm forward, and they're also canted in slightly towards your toes, which I guess would cook your toes a little bit if you left your arms straight down to the side. But what that actually does is hold your arms out to a really nice natural hover position when the engine's at full power. So we gave it a go, and this won't really look like a huge amount to a lot of you, but I mean, this was a pretty big moment for us. This was Richard only having to lean on the engines rather than having to flare them out and move them. And of course, this wasn't without its failures as well. That one, I think it was a zip tie broke that was holding the engines at the right angle. So yeah, these early stages, we're not embarrassed to say how crude these first prototypes were, because we then kind of go on to make pretty versions and more robust versions. But of course, you just got to go out and test things. So we solved the strength, and we of course couldn't just use those random bits of aluminium to fly at all these events around the world. So we designed, mostly down to Sam, I call him my engineering wife, because between the both of us, we do a lot of the rough early work, and we bicker just like a couple. So he's an amazing CAD designer, and he works on turbojet pumps and rocket engines and all sorts of amazing stuff. And this is the kind of the first generation of arm mounts that he designed. So the arm tube in the middle, the black thing, that's made out of entirely SLS nylon. And then you can see the engines, which are the shiny steel looking things, are sat inside aluminium clamshells. Now, all of this is fully 3D printed in metal. Now, for those who've never seen what it looks like, it's a really satisfying process. Admittedly, it takes days for something like the thing on the left to appear. But you have a bed of powder, and you fire a little laser over it all, turns it into a nice solid sheet, and then you add a bit of powder on top and you build it up layer by layer. Pretty cool process, not cheap whatsoever, but I think the arm mounts on the left, the fully completed ones, cost about 35 grand. Just pretty nuts, but there's kind of no other way of creating such a complex geometry that we've discovered, especially at a small scale. It works for us, and it's allowed us to make some pretty cool looking things. So this was strength solved, and back to me again. My first goes, and still wobbling around loads. I'm no Ryan, but I was starting to get the hang of it, and you could tell by my face there at the end that I was enjoying myself at least. We're making progress, still swinging around a lot, and it's always quite nerve-wracking watching people learning, because at this stage, the person who was training you had no way of, I mean, this is just me and Richard and a few others, so it's kind of down to our own risk, but we had no way of remotely shutting them down. So if they kept drifting up, they'd just bump around on the ceiling for a little bit and then run out of fuel and come down. That was what we thought would happen. We never tested that, of course, and now we have a remote kill switch, so if people start to drift a bit too high, we can bring them back down to earth. But I was starting to get it, and this is my equivalent of that first 6-second wobbly-legged flight from early on. This is my first hover. And if you can lip read, I swear a little bit, so apologies for that. But that was really effing cool for me. That's quite a special feeling, because that's the first time ever in your existence that you've jumped and you haven't come down again. You're still there, up there. Really, really weird. And then obviously I swing out at the end. So fast forward a few months, and we're getting better and better at flying. There's a team of about 4, 5, 6 of us that are going around doing events. We were doing events in Gloucester Docks. We've done, the one on the left was me flying for Gavin Williamson, of all people, for like a Navy demonstration. We did pretty amazing events that time, but it all came to a bit of a crashing end for me with this next clip. My confidence was probably a bit too high here, and the plan, this was in Serbia of all places, and we were out there doing something for the Serbian Prime Minister and President, and it was a very weird conference. I just had to meet Richard. The camera's on Richard looking at me. All I had to do was turn around, fly, and just do a loop. Aggressively, a bit too excited. And as you turn, you're spilling a lot of that thrust off, and sploosh, straight down. And I'm sure Richard's thinking, loads of expletives. And you can see I've got a deployable life jacket that's just gone off. So we even build in buoyancy into the suit, so if the deployable life jacket doesn't go off, then we're just going to sit and float. We just look like a lemon. But we had the Serbian SWAT team there to rescue me. So they dragged mournful me to the side and hoisted me out, which was just humiliating, really humiliating. Now the problem was, and this didn't just happen to me, this is Ryan, who did exactly the same thing. And it's not cheap when this happens. I'm sure one of you will ask what happens when the engines go in the water at the end. I'll try and remember to answer that. The problem was that basically at this stage, we were presetting the power of the suit, of each of the engines, and flying it entirely from thrust vector control. So if you point them down, you go up, you flare them out to the side, you come down. Point them left, you go right, so on, so on, so on. So you kind of have to, based on the climate, how hot it was, and where you are above sea level, this is quite low, this is in Reading, you could kind of guess how much thrust you'd need. And you preset that before you take off, and once you've gone, you've gone. And if I showed you the beginning of this clip, you could see that Ryan had nothing left in the tank. His arms were right down to the side, and I was pretty similar. So we needed to be able to change the power mid-flight. That was the next challenge, to be able to do a lot more dynamic flying. So this was a little calculator I made, which I don't know why I'm showing this, but it was quite a fun little app project, which worked out how much throttle percentage you want to put in your mass. I weigh 69 kilos, put 10 litres in at that temperature, and that is the arm setting on the top, the 185 newtons. That would be the amount of newtons you put on the rear engine, and that in theory was spot on, but it didn't always work amazingly. There's a lot of other things to consider. This was the old control board, really fancy, amazingly complex, could do heads-up display monitoring, it could do all sorts of telemetry, it could do RPM sensing and how much fuel you've got left and loads of amazing things. But it didn't do one pretty important thing. Voice blunt there. It couldn't do one pretty important thing, which is change the thrust as you're flying, which is now pretty essential. So instead of going back to the company that developed this and spending a hell of a lot of money developing a brand new board from scratch, I just thought, with my kind of experience playing around with Arduinos and stuff, why not we just try and make our own from scratch and just see what we want out of a system anyway. So those of you who've ever done Arduino stuff, you might recognize this. This is not even a real Arduino Nano. This is a fake one, about £3 off Amazon, and a load of spaghetti wires soldered in. And after kind of a little bit of YouTube tutorials and teaching myself a little bit about PWM and how to make faster PWM and do all sorts of stuff like that, we made a control board. And it worked, but we don't really want to test it on humans straight away, especially that mess. It doesn't exactly look flight safe. So we put it on something a little bit closer to ground. We made a jet engine powered kayak, and it's in a little box on the right there. And we had to take that on its maiden voyage. Now, luckily, one of our colleagues is ex-Navy, and he has all the right gear. So we had a little ceremony where we had champagne smashed against our inflatable kayak and all that. But it proved it worked. It proved that in operation it would actually control the engines and they'd respond right. So we tied it on the tether and it worked. And you can see here, if you notice my arms are really tight, probably quite hard to notice really, but then are flaring wider and wider and wider. This is me cranking the power until I can't control it anymore and spilling out. So that is the thrust, the dynamic thrust changing happening in person. But of course we couldn't use an Arduino for something that we were going to go around the world do demos for. It just is wrong. It's wrong in every sense. So with a little bit of help from electronics engineer friends of mine, I taught myself how to design PCBs. My dad was a massive help in this as well because he's an electronics engineer and knows all about this kind of stuff. And for those who don't know what PCB design looks like, it's great. I mean, it's literally like one of those games of join the dots. You place all your components on a board and then you just have to join all the little lines and then you hit print, well, order or whatever, and it comes through and everything's joined up. This is a little bit more complicated than the one I made, but I didn't record it. This is the board. It's great, super simple, very few things that actually kind of need to be doing anything, but it's a lot more reliable than the hardware that the Arduino comes with, and it was written in a bit of a more solid code base than doing Arduino stuff. But ultimately, it was all done kind of relatively cheaply and in-house, which is really nice, and it meant that we could do so much more dynamic flying. Being able to trim the power up and down by a couple of percent it was just a massive help. So this next video, I'm going to have a little rest from talking, is one of the flights we did out over in Portsmouth, actually, off, I think this is a P2000. This one was called Dasher. And this next video as well is in a similar vein. This was when we did our latest world record, which was back in November last year, I think it was, down at about 5 o'clock, 6 o'clock in the morning in Brighton, on Brighton Beach. Now this was, and this is a whole nother story to get into, but this was the culmination of a lot of our wing trials and testing. So if you notice, he's wearing the bottom half of a wingsuit, which we dyed orange so that you could see it a little bit better, and made essentially leg strakes, which attached to his feet and knees, and that allowed his legs to produce a bit of aerodynamic lift, and that helps massively when you start to move at speed in terms of being able to control your flight. And it's kind of like a dart; it feathercocks you in the right direction, but most importantly, lifts your legs up so that your rear engine is almost horizontal at this stage and just thrusting you forward. So this is the actual world record run that he did, and some funky music again, of course. Now, we've got a hell of a lot of these kind of clips of doing, I think we've done about 108 events now around the world in about 32 different countries. We often lose track, and we just have to count back to all the folders we've made of all the content. But if you want to see more of this footage, I think my last slide has got the links on. Follow us on Instagram or YouTube. They're kind of the channels that we put pretty much everything on. So if you're not following us already, definitely go and check that out. The main one's called Take on Gravity, and through that you can see all the other ones as well. So I thought I'd leave you with what most people want to see, I guess, in the harsh reality of it all, is all of the crashes. So this is every single stumble and fall that we've done in the past 2 or 3 years. Some of them look a bit painful, but no one was injured in the making of this video, and it's kind of a nice note to leave everyone on, that we've done this journey by taking a lot of risks, but manageable risks. And Richard always has this golden rule of, if you can take a risk and that you're not going to fail financially or reputation-wise or physically, then you should go and take that risk, because you're going to learn so much more by doing it than just kind of sitting twiddling your thumbs or thinking about things. So on that note, here is a list of a video of all the crashes.
broken 51 kilometres an hour, the record. Oh! Wow. This was one of those opportunities to learn he was good.
Yeah, I'm sure you kind of winced a little bit at home seeing that. Of course he's fine. It turns out those dirt jumps are kind of quite squidgy, I guess. So that's about it from me. I hope you've enjoyed seeing a lot of these clips and hearing this journey of how I learned to fly and the team behind it all. I've got one more video, but I'm going to skip it because I know that it's not going to play particularly well. It's a really heavy one, so I'm just going to skip through it now. And hold on. There we go. So these are the links to our socials. Mine's the Wilson, and that's the main one on Take on Gravity. And now I'll open it up to questions. I guess, Nick, if you want to jump in and start reading out any questions.
Yeah, sure. So, yeah, thank you very much, Alex. I really like the idea that you went from I'm smarter than a bird, hence I must be able to balance and fly. And I really like that as the start of an engineering project. I do really like the narrative of the whole development of the technology. So you've gone from the farmyard to world record. Yeah, that's something I really appreciate. So in terms of questions, we've got Alex. I'm a huge fan of Gravity. How did Gravity get the initial funding? As you mentioned, some of the hardware is very expensive.
Yeah, those engines aren't cheap. So those little arm engines cost like $3 or $4,000, and the one that goes on the back is about 12. So to make the first suit, Richard basically invested about 100 grand of his own money, which he'd spent the previous 16 years working as an oil trader for BP, of all things, traveling around the world, and had saved a bit of oh my God, my words. He saved up a bit of cash and has done loads of other crazy projects. He really is a brilliant inventor. But put a little bit of money into this, and then his first public event was his first kind of proper public event after launching with Wired and Red Bull was doing the TED talk in Vancouver back in 2017, I think it was. But on his way to TED out in San Francisco, he got invited to a VC's, like Boost VC they're called. He got invited to a car park and he had no expectations. He thought, brilliant, this is a great opportunity to just test the suit and make sure it works after getting it off the plane for the first time. So he did a flight in this dusty car park, and it turns out Adam and Tim Draper, who if you follow anyone in the valley of investors, they're pretty famous, if not the most famous family, the Drapers. They walked up to him with a $100 bill and wrote on the back of it a business proposition of, we'll give you $650,000 for 10% of the company, which, considering he's not even done a proper public event live yet, it was quite a crazy offer. So he put his trader hat and bargained them up for a little bit more, and there it was done. And we've still got it on the lab in the wall. So that amount of funding kind of kept us going for most of the rest of the development of it all. And ever since then, we've been cash positive based on the events that we get to do. I mean, you can get paid a huge sum of money for doing like opening the baseball season in Japan. We've done. I was out in China last, I think, October or November. I took my dad actually out with me, which is quite fun. And I was celebrating the second anniversary of a shopping centre, and they paid about $35,000 plus expenses to fly out there and do that. So most of the money we've generated has gone back into buying more engines and repairing engines, but has been generated from doing publicity around the world, which is a pretty good catch-22, I guess, in some ways. Yeah.
That is brilliant. I really like how, just an opportunity like that, going to a dusty car park, you never know who's going to be there and what opportunities that's going to those kind of things are going to present, and that getting offered that volume of money from those types of people just shows what you never know what's going to come your way. So the final question is, what is the maximum payload this system can take? Potential for fire rescue in tall buildings?
Oh, I don't fancy flying up tall buildings. Our approach to risk has always been fly as high as you'd want to fall from. So for me, that's not very high at all. Over water, it's a little bit more forgiving. But the question was payload, wasn't it? So the current suit can probably lift me in about 15 kilos, so I guess about 95 kilos. It depends mostly on how heavy your pilot is. So you might have seen in the news, I think a couple of weeks ago now, we were up in the Lake District doing some trials with some paramedics. Now, the amount of equipment that you need there is less than 15, 20 kilos if you weigh about 75 kilos as a person. So you can take a reasonable amount of equipment, but going forward to doing things like military stuff where they want to carry a lot more heavy metal stuff, we've kind of working towards that. We've been developing the next generation of the suit, which is based on the two engines that we've got, a bunch of them now, and we're building it right now. It's actually sat on the desk in the lab, and they put out only an extra 10% of thrust each, but over the course of the suit, that's actually quite a significant amount, and that means that we can lift an extra 25, 30 kilos on what we can currently do. So yeah, that's about the payload.
Okay, thank you very much. That is all our questions. So Alex has been filling the Royal Aeronautical Society slots for us tonight, and they are active in the Southwest, and all the information can be found on their webpage, which we will be sharing. So all that remains to say is a big thank you to all our speakers and the organisations they represent, and a big thank you to everyone that has attended the webinar tonight. I hope this event has highlighted some of the amazing opportunities there are out there, particularly for young engineers, and in particular how you can get involved with the engineering organisations in the Southwest that can contribute to your own professional development and help people, help people all around the world, as Holly showed. If you do want to get involved with bringing these organisations and communities together and unlocking the power of multidisciplinary engineering, we do have volunteer roles in Chain. And if you want to get involved, please do come on our website and give us an email. All of our contact details can be found on there. So yeah, thank you very much for attending, and we hope to see you again in the future.